Alright, so let's do 2015 AP Chemistry question number 2. So here's the question, and yeah, I'm gonna use it. Okay, so it says that we have this reaction, and the first question is basically asking us, find the number of moles of ethene. Okay, so let's see how we can approach this problem. So they want a theoretical yield and they want an actual yield. And so when you read the problem, you'll realize that there are two ways that you can find the amount of ethene. There's a theoretical way and there's an actual way. So the first part of A, it's asking for the actual yield. Okay, so the way we're gonna do that is by, let's see, okay, this is scrolling, okay, there you go. So first thing we gotta do is we're gonna use the ideal gas law, right? Because the ideal gas law will tell us how many moles of ethanol we have and then moles of ethene we have. So but in the ideal gas law, we always want to use ATM. So they gave us the vapor pressure of water, but they gave it to us in torr. Yeah, it says it right there, you see? So they gave us to it in torr. So we got to change the torrs to ATM, and we know there's 760. So we just got this conversion table, and we get this much ATM. So then we can find the pressure of partial pressure of ethene by using Dalton's law of partial pressures. And so, the total pressure is equal to the pressure of the individual gases, right? So the water vapor and the ethene. So we know the water vapor and we know the total pressure. And so basically it's just plug and chug, and then we get the partial pressure of ethene. Now that we got the partial pressure of ethene, we can use the ideal gas law, or PIVNERT, to find the number of moles of ethene. Okay, so then it's another plug and chug, except we use the partial pressure we found, and we want to solve for n, and boom. We just solved that using division, multiplication, order of operations, and then we get that the number of moles is that. Okay, so that's the number of moles, that's the actual yield. Now, part 2 says that they want a theoretical yield, okay? And so the key for this part of the question is to use right here when they said that the theoretical yield, right? We're going to use the 1-to-1 ratio of 1-to-1 ratio right here to here, and we know that we're going to use this fact to help us figure out the number of moles of ethene. And this is all theoretical. The actual one was using all the facts they gave us about the ideal gas law. Okay, so let's see how we did it. So how I did it. I did it like this. So first I found the molar mass because they gave us grams and we need to find moles. So in order to convert, I need to first find the molar mass. So molar mass, I just took up ethene. So where's the ethene? Ethene is C2H4. Oh no, sorry. They gave us ethanol. They gave us ethanol. Right here, they gave us ethanol, and we're gonna find the molar mass of ethanol. So it's 46 grams per mole. Okay, and then I just took the grams of ethanol they gave us and converted it to moles, and then I used the 1-to-1 molar ratio from the given reaction to get that this thing. This is the number of moles of ethene we should get according to the theoretical yield. All right, so we got our actual, we got our theoretical. Now, part B says calculate the percent yield, all right? So percent yield is just actual over theoretical times 100. And the way I remember it is percent yield is where it's at, right? Percent yield, it's like saying, right? At, and this is the important part, at right here, AT. I remember you see AT. So actual over theoretical, yeah. So it's just a saying that I remember. So percent yield is equal to actual over theoretical times 100, and we have those values. They're right up top, and we just basically plug and chug times 100, and this is basically saying that percent yield is basically saying how much yielded, how much was actually yielded over how much we expected. And so yeah, it's 60.8%. After I do that calculation, divide and multiply. Okay, what does part C say? Part C, we move on to thermodynamics. Thermodynamics, and the question is asking for the question says that, you know, we need to see if the student's claim is correct. Okay, and so he claims that basically the question is asking, does the data supports the student's claim? And what is the student's claim? The student claims that the reaction has an equilibrium constant less than 1. Okay, so we have to break it down step by step. So what else do they ask for in the problem? They ask for a justifier answer including calculation of delta G. So I'm going to start off with that. I'm going to calculate delta G, because then I can use the delta G we calculated to see what our K value is. Then we can see if the student's claim is correct. Okay, so let's find delta G. So in part C right here, first thing I want to do is that when I find delta G, I'm going to use the delta H and the delta S values. But I want the delta H and the delta S values to be the same. We cannot have kilojoules and joules. They have to be both kilojoules or both joules. But in this case, I just went with kilojoules. So I took the delta S they gave me. The delta S was right here, and they told me 126 joules, right? And so you see the delta H is in kilojoules, the delta H is in joules, right? So I want to make them the same unit. So I'm going to convert this one, because why not? You could choose anyone. So I'm going to convert the delta S to joules. And yeah, so I just did that right here. So I converted 126 joules, and I used a conversion factor, and I got that much. That's how many kilojoules are in. Okay, and then we use the equation delta G is equal to delta H minus T delta S to find what delta G is. Okay, so I used all the thermodynamic data that the problem gave us, which is delta H, 298 Kelvin, and 0.126 kilojoules, all found right over here. They just gave us that right there, and they told us they want delta G at 298 right there. Okay, and so after I did that plug and chug, I just got delta G is 8 kilojoules per mole. Okay, so 8 kilojoules per mole. Now that we have delta G, we can actually find the K value. But, you know, we can calculate it, but you can also logically think, you know, if delta G is positive, which it is, it's 8, right? 8 is positive. That means that the reaction is it's favored in the reverse reaction. If it's negative, if delta G were negative 8, then it would be favored in the forward direction. But since it's positive, it's favored in the reverse direction, backwards, towards the reactants, right? It's favored to the reactants. And the student claims that K, where is K? Where did he say it? Yeah, he claims that the reaction has a less than 1 K thing. And when it's less than 1, that when the K equilibrium constant K is less than 1, that also means that the reaction is favored towards the reactants, the reverse reaction, because that means that it's more concentrated on that side. That's why it's less than 1. If we write out the expression, we will see that. So yeah, so I went with the calculation, but then I also explained it. So first of all, so now we have all the information. We can just see what the value of K is, and then see if the student is correct. So plug and chug, and you can get a value of K. So basically, yeah, I just plug in all the information we have. I know delta G, calculated up here. The R value, we have to make sure to use the correct units, which is joules, moles, and Kelvin. Not the liters and atmospheres like in the ideal gas law. But this one, we have to use the correct units. And the units for this one are as shown. So I calculated delta G, got our gas constant, and I got temperature 298. And then now I can finally isolate this variable and solve for it. So that's pretty much what I did. Raise e to that thing, and then Kp. And indeed, I did get Kp is less than 1. And my explanation is that since the calculation of delta G is positive, that means that it's favored in the reverse direction. Kp is less than 1. And that's what also, when Kp is less than 1, it's also more concentrated in the reactant side of the reaction, and it's favoring the reverse reaction. That's why Kp is less than 1. If Kp was greater than 1, then the reaction would be favored in the forward direction, and it would be more concentrated in the product side. But it's less than 1, so that's why delta G is positive. And also, if we also using that logic along with the calculation, we can definitely say that the data supports the student's claim, which is that the student's claim is that the Kp is less than 1, and we showed that this is true. Okay, what does part D say? Part D says, draw Lewis diagram. That's about it. So first thing we want to do when we draw the Lewis diagram is that we want to find the number of valence electrons, and for ethanol, this is the number of valence electrons. So I just multiplied them, and I got 20 valence electrons. Okay, so now I just draw all single bonds, and I fill up all the octets, and then I see is that enough for is 20 is that good amount of valence electrons? Should I make double bonds or something like that? And I just made all single bonds, all octets, and I saw it worked out because we can count the number of valence electrons. Let's see, we see 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So indeed, we have 20 valence electrons. This is good Lewis structure. Yep. And now we're moving on to part E. Part E says, what is the bond angle of COH? Okay, so this is COH, okay? So the first thing I did when I approached this problem is I just think, what is the electron domain geometry, right? So how many things are around the central atom? So I see there are four things around the central atom, 2 lone pairs and 2 atoms. 2 elements rather. So I see there's 4 main things, and so the electron domain geometry is tetrahedral. And so a visual of how a tetrahedral looks like, it's like, okay, suppose this is central atom, and then it's gonna have like things sticking up. Now it's a little hard to draw in 3D, but this is basically the idea. And each of these have an equal distance from each other. The bond angles are all 109.5 degrees, as stated here. So this is the electron domain geometry. Now what happens if we decided to replace one of these elements or atoms from the central atom, and instead we put a lone pair? We still have 4 things around the central atom, except that 3 of them are like elements and 1 of them is a lone pair. In this case, we'll say we'll have trigonal pyramidal, because it's kind of like a pyramid and it has a triangular base. And we'll say that the bond angles are going to be a little less than the tetrahedral. And that's because the lone pairs, they have a little force that's making the bonds a little more smaller. Okay, so using that same reasoning, if we replace another one of these elements with a lone pair, the lone pairs will push even more on the angles, and so we'll have a bend shape that kind of looks like this on a 2D model, and it will be a little less than the one before. So I approximated it to be about 105 degrees. Okay, last but not least is F. And it says, basically it's saying that this is probably one of the toughest ones, and it's saying that like you have to say why did ethene, or wait, this is ethene and this is ethanol, okay? So it's saying why did ethene be a gas and why did ethanol go in water? So basically we put both of them in water. Ethanol dissolved in water and ethene didn't. It just stayed as a gas. You see, collected as a gas. And this is unreacted. It just stood in the water, okay? So we have to use intermolecular forces to explain. So first of all, we have to explain that ethene has London dispersion. Okay, so if we see the Lewis structure of ethene, we see that it has London dispersion. And why is that? Because to identify the type of force, we have to see like what is the difference in electronegativity. And so if we look in our periodic table, I'll just bring that up 1 second. Periodic table. Okay, so if we look in the periodic table, you'll actually just find out that carbon has a electronegativity of 2.5, while hydrogen has an electronegativity of 2.2. Now, if you subtract 2.5 minus 2.2, you'll get the electronegativity difference to be it would be 0.3. It would be 0.3. And if it's less than 0.4, which it is, then it's gonna have London dispersion. However, on this Lewis structure, ethanol, we have an OH bond, and an OH bond is a very strong intermolecular force, okay? So this is the difference. He has much stronger intermolecular forces, and he has very weak intermolecular forces. Also, if we look at it in terms of polarity, we can also see that this is a polar molecule because it's not very symmetric, you see? But this one is symmetric, right? it has the same element around the central atoms, but this side is not symmetric with this side. Therefore, this is polar and this is non-polar. Now, why does polarity matter? Well, polarity matters because likes dissolve likes. So if this is a polar molecule and we're dissolving in water, water is also a polar molecule. I'll show you that right here. Water. This is water, and water is polar. It's clearly not symmetric, right? So since it's a polar molecule and likes dissolve likes, what that means is that if it's polar, then it will dissolve in polar molecule. If it's non-polar, then it will dissolve in non-polar. That's why ethanol was able to dissolve in the water while ethene was still as gas. It didn't really dissolve in the water, like the question stated. Ethanol is polar, water is polar, therefore they both dissolve. And so I basically explained that in my explanation. I just say that first I described the intermolecular forces and explained that ethene has a weaker intermolecular force than ethanol, and basically it's London dispersion as its main intermolecular force. Because it's important to note that both ethene and ethanol do exhibit London dispersion. Almost everything exhibits London dispersion, but we're talking about the main intermolecular force, and the main one in ethene is a London dispersion, while in ethanol the main one is H bonding. H bonding is stronger, and that's why the weaker intermolecular force will be less soluble. So this one has stronger molecular I'll just say IMFs. This one has stronger IMFs. That's why it will be more soluble in water, and that's just generally a rule. If you have stronger intermolecular forces, you will be more soluble in water. Okay, and then we talk about the polarity, which is saying that ethene is nonpolar, and when you dissolve nonpolar in a polar, it's not that soluble, and water is polar and ethene is not, so that's why they're not that soluble. But on the other hand, however, ethanol is polar, and therefore would be more soluble. That's these questions. Now let's take a look at some resources. So first I'm going to quickly go over the topics. So let's start. So for the first, these are I'm going to show you on my computer the topics. So this is the AP. This is basically my resources. Yeah, so we just finished all the entire test, the entire number 2 question. Now we're going to look at like some topics that appeared in this and how they correlate with the AP handbook, and also we're going to look at and we're gonna look at the textbook pages and practice problems. Yeah, so let's do that quickly. Okay, so we have the handbook, and so let's look at the topic list. So for the first question, it was talking about gases and the ideal gas law. So we're gonna go to page 43, and on page 43 you see topic 1.1, the very foundations is moles and molar mass. This is essential because we had to know how to convert from moles, right? And this is pretty much going to be shown throughout most of the questions you see in here. Moles is very relevant because we have to calculate it. And molar mass. Okay, so 78. Okay, now page 78. So the ideal gas law. Again, this is for the first question, question A. Both of these topics are relevant to question A. The question B, I found that topic to be representations and solutions, because we were being asked in question B, we were being asked about percent yield, right? And percent yield is really just a way to represent a solution. And if we read on about that chapter, we will see this talking about like percent by masses and percent yield. Okay, so that's the topic that correlates with question B. Question C, the topic that correlates is found on page 185. And remember, that was the thermodynamics question with delta G. And there you go, Gibbs free energy, applications of thermodynamics, okay? And finding the equilibrium constant using the definition of delta G. That's the topic that corresponds with it. Let's see, 51 and 62. 51, we see in 51 we were drawing the Lewis structure, so we need to know how to find valence electrons, and we also just need to know we have to know how to draw Lewis structures, because that was the question, and so that would be topic 2.5. Okay, now moving on to number 5, we were asked about what kind of bond angle it would be. And so for that, we need to know the Vesper theory and what are the angles, okay? And that would be topic 2.7. And the final question, we were asked about intermolecular forces, and so we need to do topic 3.1 for that. And also we need to do 76, which is all talking about polarity. Topic 3.3 over here, you will see that they talk about polarity and how to determine it, okay? So those are the College Board topics. Now let's talk about the textbook. Okay, and by the way, this is the sources cited. This is just the AP Chemistry Handbook. There's the link up there, and yeah, okay, and yeah, okay. So let's look at the textbook. Textbook is right here. Okay, so I put some pages right here. So basically, it's similar to like I already told you all the topics, but I basically I correlated them to the textbook pages. These are all the readings you should do, and this is the question it corresponds to. And these are practice problems that I found useful and that are related. So yeah, these are the readings and these are the practice questions according to Nivaldo J textbook. This textbook right here. Yeah, you can find you can try and find a PDF online or use the physical copy. These pages will still work. Yeah, so thanks for watching. This was Maxim.